Hi, I'm here to present the paper Approximation Algorithms for Data Broadcast in Wireless Networks. I'm Fernanda Aparecida Silva, and I made this presentation together with my colleague Ketlyn de Castro. So, let me start by pointing out that broadcasting is a fundamental operation in wireless networks. So, even if it's a very important operation, there are problems still on uh, the action of broadcasting in multi-hop wireless networks because of the interference at the node due to simultaneous transmissions. So it's non-trivial to design a minimal latency broadcast algorithm, which is known to be NP-complete. So an example of interference is a node A sending a message to C together with a node B that also is sending a message to C. So a collision occurs and the node C cannot receive the node C cannot receive any of the messages. I would like to remind Um, there are other types of interference, like the interference of the microwave and the interference of devices that operate in the same frequency of wireless. So to not mistake this kind of physical interferences with this more related to um, networking behaviors that we are looking up in this paper. So before looking in the solution for this problem, I would like to show the related studies that the authors used as a guide to develop their solution. So first we have Shamutak and Kuten that proved that minimal latency broadcast scheduling is NP-complete for general or non-geometric graphs. Then after Chomtak and Weston, they produced an algorithm for efficient broadcasting multi radio networks. Um, the authors say in this paper they receive the insight to do their kind of solutions by looking on the improvement made on radio networks. So they used the improvements on radio networks to improve the wireless networks. So coming back to the timeline, Baksani and al. Present a mobility transparent broadcast scheme for mobile multi-hop radio networks. And then Gandhi et al. Uh, proved that minimizing broadcast latency in wireless networks is NP-complete. Gand is also an author in this paper, and in the paper that I'm talking about here, he made a draft of the algorithms that is presented in this paper. So um, it's a previous work of much importance. So in the end, William and Kemp provide a correct characterization and experimental evaluation of these protocols. So they did a study to understand how these protocols behave in a wide range of types of networks. So they gave us ground truth of the best behavior of these algorithms. So looking in more detail to the problem, the others made a distinction on the broadcast they are looking up. First type is one-to-all broadcast, is the case where we have a source and it sends a message to all other nodes in the network. And we have also all-to-all node broadcast, where each node sends its own message to all other nodes. Um, Now looking at the other solutions, we have first one-to-all broadcast. They created a 12 approximation solution that improved the approximation on the state of the art of 16 that was from the paper of Wang et al. Their improvement was made because the algorithm incorporates the following two ideas that lead to the improvement. First one is processing the nodes greedily in no increasing order of the number of receivers, and two, it's allowing nodes to transmit more than once. So their solution is basically that the algorithm takes the input of a graph in the source node S. The algorithm first constructs a broadcast tree, TB, rooted at S, in which if a node U is a parent of a node W, then U is responsible for transmitting the message to and without any collision at W. It then schedules the transmission so that every node receives the message collision-free. So now looking at the other solution for all-to-all broadcast, they deliver two algorithms. They are called CDA and ICDA with approximation guarantees of 20 and 35 respectively. They stated that the state of the art before for this kind of operation was a approximation um, algorithm with approximation factor of 27. Their improved result is due to efficient scheduling techniques to collect the data and to perform pipelined broadcasting. Specifically in ICDA, all nodes are scheduled to participate in transmission as early as possible. So CDA and ICDA are similar algorithms. The difference is that in ICDA, the nodes are scheduled to participate in the transmission as early as possible. So looking in more details to each algorithm, CDA stands for Collect and Distribute Algorithm. So in the algorithm, the graph radius of G with respect to a node V is the maximum depth of the BFS tree rooted at V. A graph center of G is a node in G with respect to which the graph radius of G is the smallest. So let S be a graph center of G and R be the graph radius of G with respect to S. We call we call we call transmissions of message M from a node V upward if the message M is originated from the descendant of V. Otherwise, a transmission is called downward. Our schedule consists of two phases. In phase 1, S collects all the packets by performing upward transmissions. In the phase 2, S broadcasts all the N packets to all other nodes via downward transmissions. Now looking to ICDA, so as we talked in CDA, we have a problem because all messages are first sent to the root node S in the broadcast tree, and then S sends the message one by one. So in the early stages of the algorithm, until S receives all the messages and start propagating them, most nodes are idle, thus increasing the broadcast time significantly. In ICDA, although all nodes participate in broadcasting as soon as possible so as to minimize the broadcasting time. The main idea is as follows. Suppose that node V receives a message MX, forwarded originally from its descendant X in the broadcast tree, and relays it to its parents to deliver the message to the root node S. Note that the children of V can also receive the message when V broadcasts it, and therefore they can initiate broadcast MX in their own subtrees in parallel without waiting for the message forward from S. So it's from this for this not waiting time, then we get improvement in practice from the ICGA in comparison to CDA. Now we are going to see the experimental evaluation of the algorithms. The experimental evaluation was made by placing a random number of nodes in 100 100 meters to 100 meters squares or more if it was desired, but it's mainly putting the a certain number of nodes in squares, so that all nodes that are close to another for a factor that at most 200 meters are expected to be able to communicate one to another. So they tried to make random compositions of networks and then to try to see how much they could communicate with each other. In this in this image here, it's the figure 5 of this paper. We can see the average latency of one-to-all broadcast. In the x size, we have the number of squares, and so the nodes of squares increasing. First, we have 100 nodes in a 700 by 700 square, and then at the end we have 400 nodes in a 1400 by 1400 square in meters. In the we have the y-axis, we have the latency, and in the lines we have first a lower bound that we are proved to not be able to improve further than that. The proposed scheme, that is the algorithm proposed by the authors, and three other algorithms that are known in the states of the art. So we can see that the proposed scheme is better than the other algorithms, and it's also reliably better. It's better in all these cases. Um, Here to all broadcast, we have the figure 7, the average approximation ratio to all broadcast. We see the same x-axis, and we have now in the y-axis the approximation ratio. We can see that at first CGA it's better, but it increases with the number of nodes, while the ICGA starts a little higher than CGA, but it's more stable as the nodes increase. So this we can see that why ICGA is better in practice than the CGA. In the end, the conclusions of the authors, here we can see the conclusion as it is in the paper. They claim a very powerful conclusion that they really gives a 12 approximation solution, that it's the reported smaller one for this kind of algorithms in the case of all-to-all broadcasting, and for one-to-all broadcasting, and for all-to-all broadcasting they gave the ratios of 20 and 34 when the known for literature was 1027. Even if ICGA has an approximation ratio of 34, it's better than the CGA because of its behavior in practice. So um, the they claim that the performance is better as it achieved a 37% latest performance improvement over the other existing schemes. So this was my presentation. Thank you.